Welcome back to the next video, everybody. Today we're going to cover what I'm calling Proposition 5 en route to proving R equals T in the minimal case. This is going to take us quite a while to prove, so this is part 1 in a series of several videos on this result. Let's get into it. Here's what the proposition says. It says, let Q be a finite set of primes with the usual properties that we've been studying over the past couple of videos. Then the Hecke algebra T sub Q is a free O bracket delta sub Q module, where this guy was defined last video, and where this module structure is inherited from RQ via the map phi Q from RQ surjecting onto T sub Q that we're trying to show is an isomorphism. Okay, so this is very difficult to show. What we really want is the corollary of this result, which we will prove today. I'll call it corollary AQ, and what it says is the following. If A sub Q is the augmentation ideal of R sub Q, then T sub empty set is isomorphic to T sub Q mod A sub Q. So this gives us a way to compare T sub empty set to T sub Q. All right, so let's prove this corollary. Consider the following commutative square of surjections. So we have a map from RQ to TQ. That's the map phi sub Q. Then likewise, we have a surjection from R empty set to T empty set. And then, of course, we have the standard maps from RQ to R empty set and TQ to T empty set. So everything is kind of functorial here, so we have a commutative square of surjections here. By proposition 3 from this chapter, this square induces a surjection from TQ mod AQ to T empty set, a free O modules of finite rank. We claim that this map is injective after you tensor the Hecke algebras here up to K, where K is the field whose ring of integers is the O that we've been working with. For convenience, we note that we're thinking of AQ here as the ideal generated by the diamond operators diamond D minus 1. It follows from the lemma in video 12.3 and the discussion that follows there that we can do this. Okay, so we talked all about this ideal. We had like almost an entire video on it. Okay, so let's let T and T sub Q be, some element that vanishes in T empty set. So in other words, take something in the kernel of this map on the bottom. Okay, denote the classes of eigenforms not in the kernel of T by representatives, let's say f sub I, and then pick one of those eigenforms f sub I. Note, for example, that f sub I cannot be in S2 of n, where n is the level of modularity of T empty set by assumption. And so f sub I cannot have trivial character. We do know, since fi is an eigenform, that tfi equals lambda I fi for some eigenvalue lambda sub I. We claim that for every one of these f sub i's with this property, that there is a Hecke operator T sub I in A sub Q, such that T sub I f sub I is also lambda sub I f sub I, whereas T sub I f sub j is 0 when j isn't I. If we can show this, we're done, because that means T is the sum of the T sub i's, and so it lives in A sub Q by definition, showing the injectivity of our map after tensoring up to K, because maybe coefficients of these guys are in K. So what we'll have shown is that if something kind of maps to 0 here, then it's in AQ here. And so then we have kind of like a first isomorphism thing. Okay, after we tensor up to K. And then we'll have to deal with what it means. We'll have to deal with establishing the isomorphism without tensoring up to K as well. So, the point is you can actually build these T sub i's directly. For each j that isn't equal to I, just find a prime q depending on j, such that A sub q of fi isn't A sub q of fj. Of course, you can do this because fi and fj are different representatives. Let capital S sub j be T sub q minus A sub q of fj divided by A sub q of fi minus A sub q of fj. Okay, this is well defined because this isn't 0. Now, fi has non-trivial character. Let's call that character chi. And then let's choose s such that chi of s isn't 1 by non-triviality. And we'll set capital D equal to diamond s minus 1 over chi s minus 1, again well defined. And then you can just check easily with a direct calculation that T sub I equals TD times the product of the S sub j's does the job. Okay, so I'll leave that to you to check. That's just kind of a do it thing. All right, so in other words, we've shown that T empty set tensored up to K is isomorphic to TQ tensored up to K mod AQ. Now, proposition 5, remember this is supposed to be a corollary of proposition 5 and we haven't used it yet. Proposition 5 implies that TQ mod AQ is free over O bracket delta Q mod AQ, which is O. So this quotient is free over O, But that means TQ mod AQ is torsion-free, and so it was actually enough to check this isomorphism after tensoring up to K by basic facts about tensor products. And so we're done. And guys, that's the corollary to proposition 5. So again, we can now relate T empty set to TQ. If you remember, we also had to relate R empty set to RQ as we've been working through the proof of R equals T. So now we're kind of working on the Hecke side and trying to do the same thing. Okay, so this proposition is going to take us a while to prove. We're going to spend, I think, like 4 or 5 videos doing it. So I'll see you during the next one, and thanks for watching.